Assalamu alaikum and hello everyone. Today, I will show you how do we identify the liquid crystalline phases part 1. Liquid crystal phases can be identified by a variety of techniques. We will discuss some of these in this slide. The diagrams on the right side. The top diagram is the spectra based on deuterium nuclear magnetic resonance, NMR analysis. We will observe peaks, unlike proton or carbon spectra that you are familiar with. The diagram in the middle is the thermogram from differential scanning calorimetry, DSC, analysis. The diagram on the bottom is the example of X-ray analysis. And the picture on the left side with textures is the phase identification based on optical polarizing microscope, OPM. OPM alone is not able to fully identify all the phases. It has limitation. Similar for the other techniques. We need at least 2 or 3 combination of methods in order to confirm the phases for sure. In lecture 2, I used generic phase diagram of liquid crystal with solvent in order to illustrate the polymorphism of amphiphilic surfactant in contact with solvents. That phase diagram was simplified and easier to understand for beginner. And also, to show all the phases that will appear in proper sequence. In this slide, shows the real phase diagram of non-ionic surfactant, dodecyl-octa-ethylene glycol with water. In this dodecyl-octa-ethylene glycol water system, we can observe that the dodecyl-octa-ethylene glycol is very soluble in water and forming micellar solution, L1. Discontinuous cubic phase, hexagonal, bicontinuous cubic phase and a very small area of lamellar phase, L-alpha. At around 65% to 100% composition of dodecyl-octa-ethylene glycol, at the temperature below 30 degrees Celsius, dodecyl-octa-ethylene glycol do not form liquid crystalline phase. Dodecyl-octa-ethylene glycol will only be soluble to form liquid crystalline at a temperature known as Kraft temperature. Based on the diagram, that is around 15 degrees Celsius where the solid dodecyl-octa-ethylene glycol soluble to form lamellar phase. At higher temperature, around 80 degrees Celsius and above, we can see the phase separation of water and micelle. In our naked eyes, the micellar solution will be clear, isotropic, and the size of the micelles are smaller than the visible range, 400 nanometer. But, when phase separation occurs, the solution will be appeared to be cloudy. That is why this transition called clouding points. The micelles are to breaking and forming a bigger micelle but, the micelles are clustering together. This behavior is characteristic of non-ionic surfactants containing polyoxyethylene chains, which exhibit reverse solubility versus temperature behavior in water and therefore cloud out at some point as the temperature is raised. Glycols demonstrating this behavior are known as cloud point glycols and are used as shale inhibitors. Polarized optical microscopy is typically used to detect the existence of liquid crystal phases in a solution. The principle of this is corresponding to the polarization of light. Please refer to the diagram on the left side of the slide. In a polarized light microscope, a polarizer intervenes between the light source and the sample. Thus, the polarized light source is converted into plain polarized light before it hits the sample. This polarized light falls on a doubly refracting specimen which generates 2 wave components that are at right angles to each other. These 2 waves are called ordinary and extraordinary light rays. The waves pass through the specimen in different phases. They are then combined using constructive and destructive interference, by an analyzer. This leads to the final generation of a high contrast image. Please watch the video on the right for clearer explanation. Liquid crystalline phase inspection by optical polarizing microscope. Before we use OPM to identify the phase, we can get some information about our sample before we can check under microscope. By looking at the visual appearance, we can see if the sample is in crystals, powder, or paste. If the sample is appeared to be paste, what about the viscosity? Liquid crystalline material normally appear to be viscous in room temperature, and the viscosity of gel is almost the same as the viscosity of cubic phase, and more viscous compared to hexagonal. Lamellar phase is less viscous. Based on turbidity, solution and cubic phase are transparent. Hexagonal phase usually fairly transparent, pneumatic phase is bit turbid. Lamellar and gel are turbid. Multi-phase samples usually very turbid, such as emulsions and non-ionic surfactant solution above its cloud point. When we view the sample under microscopy, is the sample that appear to be solid a crystal, or slightly soft, or a paste? Hexagonal, lamellar and gel phases are birefringent. That is why these phases give optical texture under crossed polars. Cubic and isotropic solution phases have one refractive index, so these phases appears to be black, no texture. Trained observer required to recognize textures. This is an art, not a science. The table on this slide shows the summary on the phase identification with OPM. Only hexagonal and lamellar will show an optical texture. Crystal will show a multicolored optical texture. In lyotropic investigation, we can use contact penetration technique. In this technique, initially, materials were heated without cover slip to dry the sample. Liquid crystal material compressed between slide and cover slip gives uniform sample. Then, place the material under microscope. The water drop place on edge of cover slip and water wicks into contact with sample. Almost immediately can be seen all phases as bands in concentration sequences, and by changing the temperature can rapidly survey mesophase range. The left side of the slide show the phase formation. The phase formation can happen immediately or may take overnight based on the solubility of the liquid crystal material. The video shows the lyotropic phases formation. These are examples of liquid crystalline phase in contact with solvent. 1 cubic phase with clear border. The material is not soluble in water. 2 cubic phase, and no clear border. The material forming cubic phase and dissolved in water forming micellar solution. 3 inverted columnar phase. 4 showing polymorphism with different concentration gradient. 5 myelin texture. 6 hexagonal phase in between 2 different types of cubic phase. 7 lamellar phase. 8 hexagonal phase. In contact penetration technique, we can see the possibility of phases that exist for the material. But, we don't have the information on the composition of the solvent or the liquid crystal material. We can study the surfactant water system without penetration. In this case, the sample is prepared with known concentration. The samples were prepared by first adding the appropriate weight ratio of the components in a glass tube, and then repeatedly mixing and centrifugation. The sample was sandwiched and sealed between 2 cover glasses. The mixtures were stored at 20 degrees Celsius for at least a week before viewing under optical polarizing microscope. For system contains imidazoline, 1-decanol, and water. At different concentration we can observe lamellar and hexagonal phases as shown on the slide. In this slide, the top pictures are examples of variation of lamellar phase that observe under optical polarizing microscope. Sometimes, the texture is clear such as in B, showing Maltese crosses pattern. But in the other picture the texture is not clear. We need another method to verify the liquid crystal phase. The bottom pictures are the examples for variation of hexagonal phase that viewed under optical polarizing microscope. Although the only clear texture of hexagonal is shown in E, the other two show more birefringent compared to the lamellar phase.